We'll go ahead and get started here. My name is Loftus Mercer. I am an architect on LabVIEW R&D. I've been there for 19 years. It's not on the front panel. My fingerprints are probably on it. About the only thing I've done to the front panel is the alignment grid long, long ago. I've been working on a number of different things over the last couple of years. And one of the ones that I've been working on the most is Malleable VIs. And we brought these in because we saw a problem with rewriting VIs, constantly rewriting VIs, in order to accommodate different data types. It was most common with the numerics. You'd write a mathematics function, and you would want an integer version, and a double version, and a single version. You wanted to keep all your precision the same, and it got worse if you folded fixed point into it. So we had all of those problems. Then you start getting the generic programming, where you want to handle a bunch of arrays. You do the same type of array manipulation, regardless of what the contents of the array are. Common handling for clusters. It was getting a little ridiculous. Okay, it had gotten a little ridiculous because I saw people doing file save as on a single VI 18 times as part of their build process. And we decided it was time to do something about this. Someone decided to do something about this back in LabVIEW 8.2. His name is Jeff Gadowski. And he forgot to tell the rest of the development team that he had added this little feature. And I found out about it in 2015 when he posted to the forums, why isn't anyone using this? Jeff, you have to tell us. So once I knew about it, we took a look at it and cleaned it up and made it productized for LabVIEW 2017's release. We're now to LabVIEW 2019. I hope you're all keeping up. But what I'm going to talk about today is going to be a basic introduction, so don't worry if you haven't. And then get a little bit into some of the new things that we've been doing with these along the way. So let's start at the beginning with the Malleable VI. Well, the word malleable means it's used commonly in metallurgy. It means something that can be shaped or bent to fit a particular thing without breaking. And these are VIs that essentially can be reshaped based on the data types that come into them. I like to point out we have malleable VIs, and we also have ductile typing, because they can be drawn as wires. There you go. You take a regular sub-VI, and you put a .vim file extension on it, and it allows the VI to become adjustable to whatever types of wire. So supposing we write this malleable VI, you can see the file extension up there at the top. Does a simple a squared plus b squared equals result. And we can write a color VI, and we can wire two integers to it, and we get an integer coming out. And so instead of doing floating point math, it does integer math. We didn't have to write the VI multiple times to get this effect. We write it once, and at each call site, it simply adjusts over. Notice no coercion dots on the inputs. The type flowed all the way through. This, at its root, is a way to write VIs that are almost as polymorphic as the primitives. And I say almost because there's a small caveat when we start talking about recursive types, but we'll get there. So how do you create a malleable VI? Well, there's two mechanisms. You can do file new ... and pick malleable VI. Or you can take any regular VI and change the file extension to .vim, and then mark it as an inline VI. All malleable VIs have to be inline. If you do those two things, now your VI that you've written once is a malleable VI. And you don't need to do anything to the callers or anything else to update them. It simply takes on those qualities. It's a pretty straightforward way to get the feature turned on. There's some restrictions on them. All the FP terms must be on the top of the diagram. So you cannot put any of your diagram terminals inside structures. They all have to be declared at the top level because they're going to adjust everything. And having conditional ones of those, there's actually some very strange effects that start popping up. And since it was a pretty good idea to put them at the top level anyway, we just decided to skip the special cases that would require a lot of weird error messages to customers and just say, put them on the top. All the controls and indicators must be on the connector pane. You cannot have anything that is display only. This isn't too much of a loss since the VIs must be marked as inline, which means there's no front panel anyway. And the VI, as I say, must have inlining turned on. Inline sub VI into calling VIs, and that implies, as you all know from your use of the VI properties dialog, that means it's reentrant, can't have any local effects, and it doesn't have any front panel. These restrictions, when I spell them out in a bulleted list, everyone's like, oh, wow, I've lost all sorts of power. It does lose some things, and there's definitely some places where we'd like to relax some of these requirements, and that's a longer-term research project. But trust me, we buy an awful lot of power, as I hope this presentation will show, even with these restrictions. They turn out not to be such a big deal as you're working with them. So we've already got some shipping malleable VIs. If you've looked at LiveView 2018, which you've already had in your hands for a while, you can find them in various places. There's one over here in the comparison palette, is value changed. It remembers the last time the value comes through and just says, is this the same value? We've got some new array functionality, including sorting a 2D array by rows or columns, shuffling a 1D array, remove duplicates. This one's brand new in 2019. If you're excited about LiveView 2019, you may have been playing around. You may have seen some new ones in the sets and maps palettes. So under sets, we wrote some basic operations as fundamental primitives, but some of the more compound operations, we just added those as VIMs. Similarly, in the maps, we have some basic primitive operations, but we have some extension functionality that we wrote as VIMs. So you can have a map regardless of what type is in the map, or a set regardless of what type is in the map. If you don't know what a set or a map is, I was going to tell you to go to Christian's presentation tomorrow, but he's been moved up to be scheduled right now. So it's a little hard for me to do that. So if you're really interested in sets and maps, I'll be outside afterwards. They don't take much time to go through. We can talk for a little bit. And otherwise, there's several presentations going on during the week. And if nothing else, you can come to the Lava Barbecue and I'll be there. Huh? And it's in Christian's is being recorded. Oh, good. So you notice these orange backgrounds that we put on them? These are just VIs. That's just the icon color. We chose that by convention so that it's easy to recognize. If you don't have to use that convention if you're writing your own VIMs, but it's a convenient notation. So, how do these VIMs work? Well, you take a VI, you call it, I'm going to use it as a sub-VI, and you drop it on a block diagram. And what happens is, behind the scenes, we create a copy of that VI. And every time you wire up a type to it, we change the types on that copy, and we see, does that work? Do we end up with a broken VI or not? And if we end up with a broken VI, then we break the wires on the collar. And if we don't, then we call it good. When you run, we run that hidden copy. I'm eliding a lot of behind-the-scenes manipulation, but that's essentially what happens. So, for example, we have a shipping VIM called stall data flow. And what it does is you have a value coming down a wire, and you've got to wait milliseconds around it, and it will obviously wait and hold until that millisecond expires, and then pass on downstream. When you drop it on a block diagram, and you wire it with a specific data type, behind the scenes we have a copy of that VI, and its type is changed to the specific type. We allow it to flow across, and you say, hey, whatever type we get on this wire, change the output to be that type, and so that's what we get up in the usage. Again, there's a lot of software happening behind the scenes that makes this not exactly the case, but it's pretty darn close. Are there any questions up to this point? Okay.
So because this code gets in line, the VI, the malleable VI itself doesn't really behave in
No, it behaves exactly like a sub-VI. That node there is calling this sub-VI. And so data arrives, executes sub-VI, data returns, passes on downstream.
So is that
No, that's this particular block diagram. Yeah, so we wrote this sub-VI. It's a common VI that lots of people have written for various reasons, but you always have to write it for save as for every type that you want. Now we've written it one time, and we can just use it permanently. Does that make sense?
Would the VIM behave the same way if you have that same thing?
Yes, it would.
And so what the CN line is that
Correct.
wrapper.
Correct. Yes.
Will the
Yes. The question was, will the malleable behavior work with units, the numeric units? Yes. Anything that's a data type will propagate through, including type deafness, enums, specifics about a cluster, class behavior, rectum specificity, all the type system that propagates through, it will come through in the outputs.
How do you define which types are the quote malleable ones?
All of them are.
All of them are. So
yeah.
You could, on that previous example, wire a double into the millisecond.
Yes.
And not have a coercion dot.
You wouldn't actually get a coercion dot. Well, you'd get a coercion dot down in here, but on your call you wouldn't. It would have adapted over to it. So here's another example. You have this one. You have a bunch of inputs. There's no plot sequence here, Jim. So we take in an array, we do some operation on it to increment one of the elements, and we can then wire it up, and we can wire in an entire array of clusters instead of an array of single. And because all of this is polymorphic for that, then the sub-VI works. So it adapts the array of double into an array of cluster, and the code works. And we only have to write that VI once, and we can use it for all these data types. So this is one that's shipping in the pallets. Does that make sense? Okay. So we can get an increment array misuse. So we wire up a string array. Well, strings can't be incremented, but let's pretend we don't know that. We look at that and we're like, well, I think that should work. Why doesn't that work? So what happened is, behind the scenes, we can figure out what happened. You can right-click on a node and say convert instance VI to real VI. And what that's going to do is it's going to replace that sub-VI with, it'll actually create on your screen, so you can actually look at it, the VI that was over there. And you can see, oh, it tried to wire a string into the +1, and so you can actually see how your text went right. I'm going to be very upfront with you, this is a terrible way to debug. I would very much like to have something that's a little less destructive, because any edits I make here are actually changing that sub-VI call, and it's no longer linked to the malleable VI once I convert it. It's now an independent copy. And what you really want to do is figure out why it's broken, and then go back to the original master VI and fix it up. It's kind of like working on your clone VIs. You find the problem with the clone, and then you have to go find the master and fix it over there. It's the same sort of annoyance. I think in the long run, and by the long run I mean NXG, we'll probably have a better solution for you. But this works, and it allows you to do an awful lot of understanding what's going on here.
It's similar to like when you have an express VI, you say show the diagram and then
yes.
destroys the express VI and
correct.
gives you one VI.
It is exactly that way. In fact, one of the ways that I like to do it is I right-click, I say convert to sub-VI, so this pops up on the screen, and then I immediately go hit Control-Z on the original VI. So it's still linked to the malleable, and then I can play with this one by itself. I wish it was a cleaner experience. Like I say, we will get there eventually. All right. I want to flip over to LabVIEW now, because PowerPoint is boring. Last year when I gave this presentation, I actually only had 3 slides, and I stayed in LabVIEW the entire time. And that was an experiment, and people said that they wanted something where things were blown up a little larger for some parts of it. So we decided to compromise here. So these are a couple of examples of malleable VIs. So we have the sort 2D array, and we've got the shuffle 1D array, and we can wire different types into them. And if I simply double-click on this, you can see I get this giant VI that I would never want to have to copy all around. And it's entirely written in terms of a 2D array of variant. Now, that call, so there's no coercion dot here. It's not converting all those things over to variants. That would be incredibly expensive and wasteful. What it's doing is it's building that specialized instance. So if I instead right-click on this and say convert instance VI to standard, then I can see that I've got my VI and it's instantiated specifically with the 2D array of strings. And if I come back over here and I do Control-Z, there we go. Now I'm linked back to the malleable VI. There's some useful functionality, like I say, in various parts of the palettes. Are there any questions up through this part?
Can I have an initialized
Yes, in fact, one of the shipping ones has that. In comparison, the is value changed. It's got the ability, it remembers the last time it was called. So that sort of statelessness is perfectly fine. But it is statelessness that's inline, so it's per call site. It's kind of like working with pre-allocated reentrancy. Okay? A lot of these examples have more code on their, or more comments on their block diagram. For the purposes of the presentation, I simplified a lot of these examples down. If you want to go through these on your own, there's a lot more explanatory text and such. So this is one the array last element, and as you can see, we can wire it up with an array, and we get a last element out. And whereas the original was written with a double, it successfully correctly propagates the integer through. What I want to show you is a couple of invalid types and what happens here. So we can wire anything that it says, hey, that's a valid thing to take, and it can be as exotic as, you know, an array of clusters, array of integers, very diverse data types. But anything that diagram underneath thinks is, you know, can successfully propagate across, then the malleable will accept it. But if you start giving it types that it can't accept, like the 2D array, well, this is the code behind the scenes, and that 2D array starts falling apart when we try to use it as an index, and they're like, yeah, that's not going to work. Similarly, you try to wire in a scalar for the first part, and yeah, that doesn't work either. Are we good on all this? What if you start doing explicit typecasting? Well, if you start doing explicit typecasting, first of all, it's still got to be a type that can cast. So if you start putting a requirement in there, you'll still get a broken wire if it's a type that can't do the cast. But if it can do the cast, well then after the cast, everything downstream is as it is. Does that make sense? Okay. But let's say you wanted to do some things that are a little bit more specific. So what if we need code that is based on data type? I.e., can I make a VIM that takes any type and converts it to a string? Well, how do you convert a string to a string? You wire it across. That one's easy. How do you convert a path to a string? Well, you need the path to string node because there's some very specific ways to format a path. How do you convert a numeric to a string? Well, that's a totally different primitive, or numeric to digital to decimal string, or possibly hexadecimal string. See, there's options you have to program in there. Every type has a different requirement. That starts to be a little bit of a head scratcher. So the answer is yes, we can. We can just go on the right. Right, dot to string. Yeah. No! Bad text programmer. Oh, man. Why do I let these people in? All right. Convert to string.vim has on its block diagram a brand new, I can't say brand new, it's a full version old, man. A nearly new structure node that some of you probably still haven't seen because you're still not using Levy 2018. The type specialization structure is kind of unique. It's a multi-frame structure, but only one frame is going to execute. So in that sense, it's like a K structure. But the order of its frames matters, which is unlike any of our other structure nodes. And what it says is, I'm going to go to the first frame, the 0th frame, and I'm going to try to propagate your type across. And if that works, I'm going to accept that frame, and I'm going to ignore the other two. And that's why they say ignored. Very helpful node, tells you exactly what happened. But if I wire up a path to it, well, that first frame hits this types must match primitive. And this primitive literally does nothing. At runtime is a complete no-op. The compiler folds it away. It does nothing. The only thing it breaks is, it breaks if you don't wire the same type to both inputs, which makes it completely useless for anything other than a malleable VI. But in a malleable VI, it's really useful because what it says is, hey, every single type would succeed in being wired straight across. But a path isn't the same as a string. So that makes that first frame only work for strings. The next frame oh, hey, that path goes to path to string, and that works all the way across. So the first frame gets declined, and it's the second frame that gets accepted, and the third frame gets ignored. Likewise, we wire a string array. Well, that's going to decline the first frame because it's not the same as a string. It's going to decline the second frame because I can't convert an array of strings, array of strings isn't a path. Which means it's going to accept the third frame, which is going to do some weird manipulation and put the strings together and concatenate them and give me a single string out. The type specialization structure helps you when you need a specific algorithm in the midst of a larger piece for a specific type.
A question about what integers and floats.
Integers and floats? Well, right now, this VI would reject all of them because none of the frames would work. And so it would hit the very last frame, and it would say, none of these work, so I'm going to decline the last frame. And so it would return a broken case. But if you continued to add more frames, then you would have it. In fact, if you want to go into LabVIEW, and you're going to go there we go. This debug log node. So I got tired of writing a bunch of debug VIs that I use a lot because I had to keep rewriting them. So this isn't actually in the palettes. It's just sitting in VI-lib. You're free to use it. And this will do anything to a string. And it's to a human-readable debug string. And it's part of a much more useful debug write string that creates a whole dialog so you can get a nice log in there while you're debugging. Feel free to take a look at that later. But for the purposes of your question, I had to make it spell out a whole bunch of types and teach it how to handle some integers and paths and format the only good, correct format string for a timestamp. Thank you, Lava. There's a great debate about the right way to format timestamps on Lava, and there was a consensus that is the format string, so I used it. Yeah, and then there's a final case down here that will accept anything, because it'll go to, it uses the write to XML, so as a final all case. Does that answer your question? All right. About how to, oh yeah.
I assume the order doesn't matter.
The order of the frames does matter. We'll try them in failed case order. So it'll start at the 0th frame and see if it succeeds.
Oh.
So if you have a frame that would accept multiple types, it'll take the earliest one.
Oh, so you have to go something to
Right. If you had two frames that would both work for, say, paths, it'll always take the numerically earlier one in the frame order. That's why I say this is a unique structure in that it's the only multi-frame structure in LabVIEW where the order of the frames does matter. Okay. Yes. Two different classes will be treated as they are not the same type. It actually says must be the same type. It does ignore type deference. It cares only about the underlying type, and it. I've forgotten whether or not it cares about the names of cluster elements. I actually don't remember. You have to check the documentation. But I know it ignores type defs. It'll allow the type through as just what the type means. All right. So malleable VIs. So now you've got the basics. Now you've got where we were when LabVIEW 2017 released. Now we're going to talk about LabVIEw 2017 SP1. In SP1, we fixed what should have been in 2017. We got the last bit of cars and we turned on a new feature, which we don't usually do in an SP1, but it was so close. And we taught them how to adapt to classes. So I can write a malleable VI, and I can stick some some class methods in there and make them, well, fun. Let's go take a look. So I wrote this sub-VI, run thermal tests. And I have a cooling system and a thermal sensor and some test cases wired in. And if we open up the VIM, master copy here, it does, it takes the test, it says read the starting temperature, cool until we hit that target, run whatever the test is, read the resulting temperature from the sensor, and then check the result. Not particularly exciting, wasn't meant to be exciting. The next frames look more exciting. All right, and then we can use that here. You see, I wired up the cooling system and I wired up the thermal sensor, and that's in the those are just generic types. Then I wired up this very specific class that's the evaporative cooler and the J-type thermocouple, and I did the same run test. Now, you're thinking, oh, okay, fine, Stephen, who cares? That's all dynamic dispatching and inheritance and blah, blah, blah. Yeah. No inheritance. I'm able to write a malleable VI that can take a generic setup that just says you need to have classes that have the following methods. No details about what else has to be in there. They just need to have these methods. And then as long as they have those methods, I can wire them up and the malleable VI will accept them. Because what's happening, if we look at the actual instantiation here, is it goes through and it says every method, comment it out, and replace it with the specific method for the specifically wired class. So you can see that, we had one that was for the generic, and it got swapped out for the specific evaporative cooler. This ability to just adapt to methods essentially means that you have a core form of interfaces. Now, it doesn't fulfill all of the use cases for interfaces, and we still need real type interfaces in LabVIEW, and I assure you, finally I get to tell you, they are coming. They were on the roadmap this morning, and we are actively developing them. But this static analysis, this ability to write a VI that will adapt to the particular methods, can solve an awful lot of your use cases today. And it can significantly reduce the amount of code that you're generating and give you a nice separation of behaviors between this is my basic implementation and these are my concrete instantiations, and I don't have to have a common root parent for all of that. And it allows you to do some really interesting things, because where I can take that node, I have a compressor cooler that has a sensor built into it. And so it's both the cooler and the sensor all in one. And I can simply fork that wire to both terminals. And it's essentially as if I had, well, not quite multiple inheritance, but I had the functionality joined together. I was able to pull both of them in and just use it. And if I look at the instantiation from the point of view of the internals, that one class, you can see both terminals are the same type on the instantiated method. Again, not everything that we want to have with interfaces. Certainly doesn't give you dynamic typing, doesn't give you heterogeneous arrays, la 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 la. But write once, use for many independent systems, separation of concerns, this is a big win. And you can use it for an awful lot of things, and it's decided all at compile time. So there's no runtime overhead for dynamic checking or anything else. It's all just compiled in. We've simplified and improved a number of test systems around various customers with this little feature. Any questions here?
I think you mentioned this a little bit already, but what is the advantage of not needing a common parent?
We're not needing a common parent. There's a thing called the fragile base class problem. You end up with, when you have one test system, and it needs a cool until temperature and a read temperature function, you end up, it's easy to have a base class, you put those on it, and everybody sends. But then you have another test, which the same piece of hardware is going to go to, that needs something else, like check voltage, or run motor. And you start putting all of those onto the same base class. And this base class becomes more and more of a pocket knife that is both unwieldy and you can't figure out which blade you need. And when you can separate those out into, this is all I need over here, and you just give the thing only the functionality that it needs, and it can go to wherever that happens to be acceptable, that's a major win for independence of causes. Does that make sense?
Yeah.
Back there?
How does this interact with like PPLs? If this is all at compile time?
This is all I compile to. So VIMs can be inside PPLs, they cannot be exported from a PPL.
Okay, so I couldn't make a plugin. For example, if I compiled the first thing that you showed and then I added my sensor plus evaporative cooler as a plugin, that wouldn't fly.
Correct.
Okay.
Yeah, they are compile time decided. Again, we need true interfaces for some use cases.
Well, one of the things I think was commenting is trying to dynamically dispatch PDFs.
Trying to dynamically dispatch PVRs.
So one of the things I foresee is deadlocks.
Mm-hmm.
And how do I go about debugging that if there's just been drafting for time?
It doesn't really change anything. I mean, if you ask, so the question is, how do you start debugging, the problems with PVRs and deadlocks and everything? It doesn't change anything from how would you debug anything else with the malleables. How do I get my array algorithm right? Well, I'm showing you the convert over, the test it in different phases. You can actually rewrite the malleable VI itself, just change its types, because it literally doesn't care as long as the type successfully gets across which one it is. So none of your callers will break. So that's another trick you can use to debug these. Whatever approach you're doing, that doesn't change. The fact that you're using DVRs and worried about deadlocks, that's the first thing to debug, is why are you using them. But no references, not unless you're forced to. But when you're in one of those cases where you have to use them, the techniques involved aren't any, there's nothing special there. Does that make sense? Okay. Quick plug. Examples, channels, replacing the function at the heart of an algorithm at runtime. If you are anywhere near an architect level who's designing larger scale systems, I would like as many people as possible to look at this shipping example. I put it in for the first time in NIWeek 2015, and I've added to it over the years. It's no longer got necessarily much to do with channels, but I don't want to move it because it does use channels quite a bit. But it's got a whole bunch of different techniques, and the malleable VIs is another technique that I've folded into it. So if you are at all interested in different ways of handling runtime polymorphism, independence of code, plug-in substitution, and adaptivity of VIs, please take a look at that shipping example. It's one of the more interesting that I've ever put out there. Like I say, it used to be channel specific, and I've created a lot more functionality than just that. All right. So, where we go next? Oh, I want to do, okay, I do want to get the last piece here is this final shipping example. So, nesting malleable VIs. When you have a malleable VI that's going to call another malleable VI, it works just fine. They cascade down, they'll instantiate. But I want to show you some cool techniques we can get with that, some neat effects. So this is my shuffle 1D array VIM. My first naive approach. What I want is something that will allow me to shuffle, and I can wire in whatever type I want, and it will end up shuffling them around. Let's talk about the ones that are bad ideas. So this works. You notice I've got this type specialization structure here. And then I've got some code. This was lifted directly out of Shuffle 1D array. And what I'm trying to write is, well, let me show you from the front panel here. We're trying to take a malleable VI, and we want to do some very specific things with the elements. So we have Shuffle 1D array. It's a working function. But what if I wanted to teach a string how to shuffle and retain whole words? Or I want to shuffle a path, and I want to end up with the paths like the individual segments of the path. I can't just convert it to an array and sort it. I've got these special rules for what I want to do for each of the data types, right? And then once I've done my shuffle, I need to put it back so that it becomes a path once again. So that means I have a common operation, and I have a specific data type aspect to it. The rule that I want you to walk out of here, even if you don't understand what I'm about to show you, is whenever you have an operation of a container type and a separate operation of the element type, make them two separate VIMs. Make the first one a VIM on the container, and have, anytime you're doing something specific with the element, create a separate sub-VIM inside. You'll be way more successful. Even if you don't understand what I'm about to show you, and you don't know why you're more successful, you will be. All right. So here's the first problem. So I want to do some specialized code over here for, okay, if it's a string, I'm going to change it to a byte array, and then go shuffle it. And then if it's a path, I'm going to change it into, change it to a path to string and put its pieces together. And then if it's an integer, I'm actually going to break it down into its separate component pieces and build an array of those, and then I'll go shuffle that. All right, so that part works. I've got specific code for these three. And the problem is when I want to put it back together, because the 0 case will be accepted for all of these types, because it's all being converted to an array of bytes. In all these three cases, the type that comes out is an array of bytes, which means this one is always going to accept frame 0, so I'm always going to get a string type out no matter what type I put in. And you fight with this, and you fight with this, and soon you realize you've got to have something over here that forces the type. And so then you get this bright idea. And I know you get this bright idea because I put this in front of customers and asked them what their next idea was, and yeah. Let's see. Come down here, and we start putting specific magic code in each of these frames. And so we have the code up front that's deciding to do something on each of the different types. And then we come over here and we put code into each of these frames that is, okay, this will only work if the original type was a string. And this one will only work if the original type was a path. Notice we're not even wiring the output of this. We're just trying to cheat to get a broken wire. And so what you end up with is this pairing of code. Every time you add a frame over here, you have to go add a frame over here, and you have to do something special to get this extra. And it's kind of silly. For one thing, when you've got debugging turned on, you're creating an extra data copy, which is problematic. The compiler will get rid of it at runtime when we turn off debugging, but still. This is really hard to maintain. You've got duplicated code in both places. It's not really flexible. You really want something that is going to convert over and convert back and know how to do that. Does everyone see the problem here with the duplicated code and how to do maintenance? All right. You can't really link the structures. Yes, it doesn't. Conceptually, there's not a good way to tie this together. And actually, we have worked through what you would do to do that. It's not really you end up with a lot of very strange errors about, this one has more frames than that one, or how do you prove orthogonality between the two? There's some odd cases. And we were going to work on trying to do some sort of linked structure, but what we realized is the nesting of VIMs, what I told you to do, is just cleans up the code. So if we go look at what the successful one is, the successful one says, hey, look, I'm going to write one structure node that has the instructions for how to tear it apart, calls my common sub-VI, and then knows how to put it back together. And now I have all the code that is type-specific, all in one place, all tied together, no special forcing functions, and a very clean implementation that you can understand without having to try to keep paired parts of your code up to date. I've also been able to fully reuse my shuffle 1D array, which is a generic piece that is useful in other places, rather than copying its code out. So when you look at any time you've got, like I say, something specific to the element and something common to a container, splitting those into two VIMs would be a lot more successful. Yeah, I still got time. So we added a bunch of functionality here for searching and sorting. So this is the search 1D array primitive that you're all familiar with. Everybody's used it. This is search unsorted 1D array. Has exactly the same functionality. It does a linear search down. Nothing particularly earth-shattering there, until we start looking at this extra terminal that it has. So where search 1D array doesn't have a bottom terminal, this does. And I can wire in an equals primitive, and I can say, hey, I'm going to write a function down here where upper and lower case are treated as equal. And now I can do a search 1D array, and it will find that second entry. Being able to override the equals operation for search and sort is a big deal. How many people have ever had to write a custom search routine because they needed the second element of a cluster? Yeah. How many have ever wanted to sort on the a part of the string, say the last name embedded in the string? You have to do all this, break it apart, then sort it, then put it back the other way. Yeah. This allows us to specify, I would like you to use this function as my comparison. And I'll wire it in, and as long as it has the right connector pane, this will accept it and it'll work. Similarly, instead of wiring a sub-VI or a VI reference, we can wire a class that has the method in it that we need, that this has an equals method. And this one actually specifies a regular expression. And so now we can find and do a regular expression match with exactly the same sub-VI. Fun fact, when you don't wire that additional terminal, they have the same performance, the primitive and the search unsorted. When you do wire it, your overhead is, well, the extra comparison that you've got. But otherwise, it's the same thing. So that's kind of nice. These, if we start opening this up though, the first thing we'll see is, how do I guarantee that it's the same performance? Because if you don't wire it, I turn around and call the primitive. So, basically make sure that there's no way in heck that we're going to get through here with, losing performance. But in these other frames, I can check to say, hey, did you give me a class that has a well-defined equals operation? Okay, then we'll just use its equals. Did you give me a comparison function override? Okay, we'll use that. Did you give me a VI ref node? Then we'll use that. If I open up this core function, this is my search. Remember, this is my generic part of my array. This is for the container. And this is the specific equals operation. That's working on just one element. And it's checking to see, as we linearly walk through, is this equal? And it's going to use whatever I told it to use. So if I have a default equality, then we're going to just try to use the equals of the type that comes in. So if it's a class and it has its own equals method, we'll try to call that. If, on the other hand, it's not a class, but it's still the default, then we'll try the plain equals operation, the standard equals compare. If that doesn't work, then we're going to call this equals VI, which is an operation on the functor that you passed in. And if that fails, we'll try and see if it works with the call by reference node, because maybe you gave us a VI reference. And all of that trying is all done at compile time. So we'll know, by the time you hit run on this, which of those frames is going to execute. And so there's no extra overhead from all of that. It's all compile time check. And this is my little extra piece here, because some person figured out that they could slip other functions in that would give results other than a Boolean, and play some really interesting games. And I'm like, that's not supposed to be part of the API, and I don't want you playing with it like that, because that makes it hard to refactor code. So I put an extra assert at the end that whatever it is better be giving me back a Boolean. These VIs, many of them are, so you can explore this nested malleables presentation more and go into greater depth on it. You can get some really cool effects. search and sort algorithms that allow you to maintain sorted arrays, doing some filtering operations where you pull all of the things that you want out to the front. You get some really advanced algorithms out of reusing exactly the same code just by putting ever more clever functions into the comparison. These are not in the palettes, all of them. Some of them are. Some of the others are sitting in VILib/array. And I'm going to put them in to the palettes as official supported things in LabVIEW 2020, I hope, assuming that they pass all of you guys as use cases and you guys play with them a bit and give us feedback and go, yes, they all look good. But they're there for you to use in the meantime. They pass all of the tests I've been able to throw at them. I have Christian Altenbach. I've already asked him. He's trying to put performance numbers together to make sure I actually hit all the performance targets. He's rewritten these VIs many times, so he's a good expert to bounce things off of. But then we wouldn't be doing this if many of you hadn't rewritten these on many occasions. So many of you are experts in it. So take a look at them. Let us know if they really work, and if they do, we're going to shove them into the official palettes. So, hopping back here, finish this out. Since I got, according to the schedule, I got 15 minutes left. Let's do some facts here real quick. Before I go call for general questions. How do malleable VIs differ from poly VIs and X nodes? If you don't know what an X node is, don't worry about it. It's this weird religion that some people believe in. These lava people are, oh yeah, the X node. Yeah, no, not a thing. Malleable VIs are much more simple. They're more scalable. That wasn't entirely true in LabVIEW 2018. In 2019, they load very fast, and we've gotten rid of a lot of the performance headaches that they were creating when you start stacking them really deep. And we've really pushed some of the boundaries on them. You can nest malleable VIs one inside the other, as we've been showing in the previous. You cannot put a malleable VI inside a poly VI, and the reason for that is the poly VI wants to pick one of the signatures. Well, a malleable VI doesn't have a particular signature. And while in theory we could try some different ways of attempting it, all of the ways that we've proposed, we haven't really liked the effects. There have always been some weird special cases or selections that are hard to explain why it's picking that particular one. If you got a good idea on how to bring these together, and you really think we need to be bringing them together, post on the forums. But now that we have the text specialization structure, there's a lot less need for us to bring them together. So there's still a nice case for the poly VI as being used to explicitly select an algorithm. But we think we can handle that with some other effects, particularly when we start talking about NXG.
So when you say you can't put a malleable VI inside of poly,
I mean, as far as like make it one of the things that the poly VI has. Yeah, in the configuration ring. Yeah.
Is there any reason to try the poly VI?
Yes, that algorithm selection mode. Like when you want to drop a node and it's not changing based on its types, but you've got you want to have the little drop ring for square wave versus sine wave versus triangle wave, because you want a generator. That sort of algorithm selection is still a pretty good use case for them. Also, if you need a poly VI that isn't inline for some reason, like a poly VI on dialogues or something. I've never actually seen anyone write one of those, but it might be a use case. Can I make a VIM that only accepts unsigned integers? As we were showing, the assert specific type function allows you to do that. There's also a bunch of assert VIMs already in the palettes that will tailor in different ways. So there's one that says only integers, only unsigned integers. Allow anything that looks like a numeric, including waveforms, this sorts of things. So you don't have to rewrite those asserts. And we've pulled an awful lot of people. At this point, I've gone a full year without anyone asking me for an assert that isn't in the palette. So that's a pretty good sign that we've covered pretty much the big use cases. And if you need one that's specialized, take a look at how they're written. You can write your own. What happens if I save for previous? All those instance VIs, they get turned into real VIs. And if you save for previous, obviously before 2017. So 2018 and 2017, they're fine. Save for previous into 2016, they turn into regular VIs, and the VIMs lose their IM. Let's see. Will malleable VIs be available in LabVIEW NXG? Yes. We don't know exactly when. They're operating on their own timetable. We're moving both products forward at their own rate. Obviously, they're accelerating past us because they have a much larger dev team. And when they're ready to bring these features on board, they will. Can I have a recursive malleable VI? This one gets asked a lot. So a recursive malleable VI would be what the magic that happens on, say, the add primitive, where you can have an array, a cluster of array, a cluster of array, a cluster of array, etc., of integer. And you can wire that up, and the plus sign knows how to unpack, okay, index, and then unbundle, and then index, and unbundle, and it can unstack all the way down in order to add to that structure. If you wanted to write a malleable VI that is that polymorphic, it cannot currently be done. You can do some tricks to make it unroll to a specific number of levels with the type specialization structure, and you can play some games there. But ultimately, it doesn't unroll nearly to that degree. Research is in progress. Something we'd like to have at some point, but it's kind of a low priority compared to some other things that we have in the pipeline, interfaces. And we may or may not get back to it anytime soon. We haven't heard a whole lot of demand for it. What we've got with Malleable VIs today seems to have satisfied the 80% use case and has unstuck a lot of people who have been writing mathematics libraries and some of those other use cases. Do I have any questions? Because they're inline. And even if we turn off inlining, there's still a concern. We have to have a static way of figuring out how many times do you have to keep instantiating it before you get to a stable type. Proving that the type settles is a hard problem to prove. And if you just let it run and a customer has written one that doesn't settle, you end up blowing up memory. So you need something that is a higher level proof function to prove termination, or you need an arbitrary termination boundary. So you play some games in there. But the big limitation is that the inlining is hidden. Any other questions up to this point?
I would recommend type specifying an enum.
Do I recommend type specifying an enum?
How would you?
How would you? So the assert type ignores type deafness, but it pays attention to the underlying type. So you can just wire that enum there, and you could wire the type dev version of the enum if you want to keep it up to date. Oh, arbitrary enum? Arbitrary enum you can't do. The closest you can come is a format into string primitive wired with a %s. That is the only function I know that will reject the enum, will reject integers but accept enums. All right. Before I let you go, would like you to strongly consider taking a survey that we've got. We are offering a $25 Amazon gift card to the first 200 folks who respond and completely fill out the survey. We want to hear from those of you who are tinkering with software, who develop in your own time, outside of the office, the home developers. And these are some questions about how this influences the tools you choose to use at home. And not to give the game away or anything, but it may be some questions along the lines of how much can we go making this available for home use? And by this I mean the LabVIEW ecosystem. So if you're interested in that sort of thing, we'd definitely like to hear from you. There's some internal lobbying going on, and we'd like to know what the community thinks about it.
On your nested malleable VI example,
Yes.
You were talking about how you end up with two malleable VIs instead of just the one with two different structures.
Right.
All total in that example, so did you have 3 malleable VIs, the one on the top and then the 2 in the middle, or was it just those 2 in the middle? I wasn't sure. Did you have 3 all total, or it was just
I showed 3 different versions, 2 bad examples and one good example.
Right. So on your good example, where you show the 2 nested malleable VIs, the one on the top is a malleable VI as well.
Yes.
Correct?
Yes.
So you have 3 malleable VIs that are all total. Is that correct?
Should only have 2 malleables. The number of instances is 3.
No, that's
Okay, yeah, the instances is 3. Yeah.
Okay. That might be my question.
Okay. So one there, one there, one there. And so each one of those is instantiated for its specific type. 2 of those frames are commented out in any given compile, so they're not necessarily instantiating.
So in the equals substitution that you showed, that seems like it could be pretty dynamic, right? I could supply a VI reference that I loaded beforehand as long as it adhered to that
Yes.
connector pane?
Yes.
Or a class that I loaded from disk? Cool.
Yes. So yeah, you can plug in dynamically to change your capitalization detection, or one of the examples has an equals comparison with an epsilon, and you can programmatically set the epsilon. In fact, that's covered in the shipping example to show you how to do that. Yep, I've got the time here.
Curious about the use of malleable VIs.
Mm-hmm.
So, one question I have, we already presented on like how to malleable VIs for interfaces. Is that available anywhere?
So if you walk through the presentation there in more detail, the actual shipping example has a lot more comments than what I had here. I stripped them out so it would be on the screen easier. So if you read through that, it's got a pretty good explanation of what's going on there.
So in general, we use that for kind of
Your template classes.
That has a method.
Right.
And then you create a malleable VI wrapper around each method.
Right, so your malleable VI would be your algorithm that you want to run, whatever operation, and you create some template classes that have the specific methods that are needed. And you would write your malleable VI in terms of that, and then you would use your malleable VI with the actual classes that happen to have methods of the same names. I have tended to do so. The template classes and the malleable VIs that they're templating, I have tended to put them into a single library together. Tended because I didn't do that with some of the array ones that are in VI-lib, because I wanted to be able to reuse those comparison procs and equals procs in multiple different tuple VIMs without tying it all together. So I don't have a strong recommendation for yes, do this, but consider do this. On the don't avoid, consider do scale, it's a consider.
And so just in terms of application, so this would be like kind of purely edit time interfaces with a specific.
When you know the specific interface that you need to talk to, yes. Correct. So, and that's the hardest thing to keep in mind with all of these things about malleables. Everything's decided at compile time. So when you find yourself fighting with it and you're like trying to do runtime plugins and everything else and you're posting on the forums, it's all static time.
This feature real time. I was told it didn't work for a while, and we've got a couple headaches here and there.
As far as I know, at this juncture, there should be no problems deploying them to real time. There may have been some deployment issues in 2018, 2017, but I thought those were even all resolved in 2018. My memory for exactly when cars got fixed is a little foggy, but I thought that 2018 was completely clean there as well. So double check that, but I'm pretty darn confident because we got a lot of exercise on them in 2019. Anyone else? You've got about 60 seconds left. All right, then I'll let you go early. Thank you for coming.